Look at this terminal animation. What starts as a jagged, chaotic data signal rapidly smooths out, collapsing into a mathematically perfect repeating curve. In our previous module, we defined the sine wave, a curve that oscillates evenly around a center line. Now we introduce its counterpart, the cosine wave. The Fourier transform relies on both of these functions, operating together as an inseparable pair to model physical reality. The cosine wave shares its exact geometry with the sine wave, but begins its cycle at a different position. Geometrically, if a sine wave tracks the vertical height of an object moving in a circle, a cosine wave tracks its horizontal projection. This plot displays the complete general wave equation. To understand how engineers use this formula to manipulate physical systems, we must deconstruct it. We will break it down piece by piece, defining 14 specific notations, starting from basic geometry and ending at the Fourier series. Mastering the architecture of this single equation provides the mathematical vocabulary required to decode digital signals, alternating currents, and cyclical markets. This diagram shows a unit circle, a circle with a radius of exactly 1 plotted on a Cartesian grid. As a point rotates counterclockwise, we track the length of the horizontal line connecting that point to the y-axis, tracing it out to the right. The vertical position on this resulting graph is defined as y. This represents the instantaneous output of our function, which translates to physical measurements like electrical voltage or the current price of an asset. The mathematical engine driving this output is cos, or cosine. Historically termed the complementary sign, cosine acts as a mapping machine. You input an angle, and it outputs the exact horizontal position on the unit circle. In calculus, the relationship is defined by differentiation. The derivative of a sine wave is a cosine wave. This means the cosine wave maps the instantaneous rate of change of the sine wave at any given point. The input for this machine is theta, representing the angle of rotation. You can remember the symbol because it resembles a horizontal line cutting through the center of a circle. Mathematicians and engineers frequently use x interchangeably with theta on static graphs, using x to represent the horizontal position along the wave's path. We measure this horizontal distance in radians, specifically pi and 2 pi. Derived from the ratio of a circle's circumference to its diameter, exactly 2 pi radians constitutes one full 360-degree rotation. Let's test this geometric logic. Look at the traced wave. At what specific radian values does the cosine output crosses exactly through 0? It crosses 0 at pi over 2 and 3 pi over 2. At the absolute top and bottom of the unit circle, the point has 0 horizontal projection. If we calculate the output at the very beginning of the rotation, when theta is 0, the horizontal distance from the center is exactly the full radius of 1. Because the cosine of 0 is 1, the cosine wave starts at its absolute maximum height. A sine wave, conversely, begins at 0. The geometry of the cosine function converts uniform angular rotation into a linear measurement of horizontal position. Look at this adjusted animation. We are replacing the static spatial x-axis with a dynamic t-axis, representing time. We now have two parallel waves moving at completely different speeds. T stands for time in seconds. It is the fundamental independent variable used across physics and signal processing to map how a system evolves. Capital T is the period. This is the exact duration, measured in seconds, required for the wave to complete one full 2 pi cycle. F is frequency. Measured in hertz, frequency counts the total number of complete cycles that occur within a single second. Frequency and period are inversely related. Frequency equals 1 divided by the period. If a cycle takes half a second, its frequency is 2 hertz. Next is omega, known as angular frequency. Instead of measuring cycles per second, omega measures how many radians the wave travels through per second. We translate between standard frequency and angular frequency using a specific multiplier. Omega equals 2 pi times f. In mechanical engineering, omega dictates the rotational speed of a system. For an alternating current generator, omega is the rotational speed of the turbine spinning inside the magnetic field. A generator spinning slowly has a low angular frequency, producing an elongated voltage wave. A turbine spinning rapidly produces a compressed, high-frequency voltage wave. By injecting time, period, frequency, and angular frequency into our mathematical formula, we translate a static geometric drawing into a continuous, active rhythm. This animation demonstrates how we scale a wave's physical magnitude. The rhythm remains continuous, but the proportions in both the vertical and horizontal dimensions are stretched. The variable a defines amplitude. This dictates the maximum absolute displacement of the wave from its center resting line. Note the specific geometry here. Amplitude is measured from the center line to the peak. It is not the total distance from the bottom trough to the top peak. If we apply this to financial market models, amplitude maps the peak volatility spread. A higher amplitude represents a wider swing in an asset's cyclical price. Lambda is wavelength. This represents the physical, measurable distance in meters between two consecutive peaks as the wave exists in space. V represents wave speed. Just as a car speed is distance divided by time, a wave speed is its wavelength divided by its period. Because period and frequency are exact inverses, this equation is identically expressed as velocity equals wavelength multiplied by frequency. Amplitude, wavelength, and wave speed govern how much physical energy the wave carries and how rapidly that energy propagates through a medium. When analyzing multiple signals in a single system, the critical variable becomes alignment. We have to account for waves that begin their cycles at different starting positions. Look at this plot comparing a blue sine wave and a red cosine wave. Notice that their structural anatomies are identical. As the blue sine wave slides exactly 90 degrees to the left, it perfectly eclipses the cosine wave. The parameter controlling this horizontal offset is phi, known as the phase shift. It defines the specific starting angle of the waveform. This visual alignment proves a central identity. The cosine of theta is exactly equal to the sine of theta plus pi over 2. This confirms that a cosine wave is a sine wave shifted 90 degrees to the left. In electrical engineering, this 90-degree offset is physical reality. When alternating current runs through a capacitor, current leads the voltage by exactly 90 degrees. Therefore, if you model the circuit's voltage using a standard sine wave, the leading current is modeled by a cosine wave. Phase shift is the definitive mathematical parameter that distinguishes these two functions, allowing us to model components that operate in a constant state of quadrature. We have now assembled the complete general wave equation. We can calculate its amplitude, angular frequency, time, and phase shift. Look at this plot of jagged, volatile stock market data. Theoretical mathematical models are perfectly smooth, but real-world data is inherently chaotic. Real-world signals, whether they are audio recordings, radio transmissions, or price fluctuations, are rarely perfect solitary waves. Fourier analysis reveals that any periodic signal, no matter how jagged or chaotic, can be mathematically deconstructed into a sum of simple, scaled sine and cosine waves. This presents a logical tension. If sine and cosine are just shifted versions of the same shape, why does the analysis require both of them to reconstruct a signal? The requirement stems from structural superposition. Sine functions capture odd mathematical symmetries, crossing perfectly through the origin. Cosine functions capture even mathematical symmetries, starting at their maximum peaks. Together, sine and cosine form an orthogonal basis. They act as a team that can map the exact amplitude and phase of every frequency buried within a complex signal. By deconstructing the 14 distinct notations of the cosine curve, you have acquired the foundational building blocks required to analyze, filter, and process any complex system in physics and engineering.